Hello everyone, welcome to the lecture series on basics of electrical engineering. In this video, we're going to see the worked examples on series RLC circuit for AC supply. So one of the prerequisites for this particular solving problems on series RLC circuit is to see the theory behind series RLC circuit. So it's already explained in one of our videos. Please do watch it. The link will be provided in the description. There are 6 different problems solved in this particular video, and all of them seem to be different from one another. So once you solve all these 6 problems, definitely trust me, you will be having great confidence in order to approach series RLC circuit related problems. Alright, so let's get started. Example 1. A resistor of 20 ohm and inductor of 0.05 Henry and capacitor of 50 microfarad are connected in series. So they have directly mentioned that they are connected in series. It's a series RLC circuit. A supply voltage 230 volt 50 Hz is connected across the series combination. Calculate the following: impedance, current drawn by the circuit, phase difference, and power factor, active and reactive power consumed by the circuit. So how do we approach these type of problems? So they've mentioned that it is a series RLC circuit, so we don't have to scratch our head as what type of problem this is. So first off, let's write the given data at a particular place. 20 ohm resistance, inductor of 0.05, capacitance value, voltage is 230 volt and frequency is 50 hertz. So we will be drawing the circuit diagram for our convenience in order to see how it looks like. So once this is done, we will be starting off. Our first step is to find the impedance. So the impedance can be found out in this particular fashion using the formula, that is Z bar is equal to R plus J into XL minus J into XC. So we have to find the value of XL and we have to find the value of XC as well. So we'll be finding that, and then we'll find the value of Z bar. So XL is equal to 2 pi FL. So 2 pi into 50 into the inductance value that is given as 0.05 Henry. Substitute, you will be getting 15.71. So we know XC is equal to 1 by 2 pi FC. Substitute for the values, and you will be getting it to be equal to 63.66 ohms. So once we know XL, once we know XC, we can substitute in this particular equation and find the value of Z. So Z bar is equal to R plus JXL minus J into XC. Substitute, you will be getting it to be equal to 51.95 at an angle of minus 67.36 degree. So it is very clear, the magnitude and phase angle is given. So if we are considering only the magnitude, we can represent Z is equal to 51.95 ohms. So once this is done, our next step is to determine the phase difference. So we don't have to scratch our head in order to determine the phase difference, because the phase difference is directly given here, that is phi is equal to 67.36 degree. So we don't have to mention the phase difference as minus or plus. We can directly take the value whatever is there, because it only gives you the phase difference between the voltage and current. However, we can say with respect to power factor whether it is leading or lagging. So our next step is to determine the current, that is according to our given question. So I is equal to V by Z. So we will be substituting the value of V and we know the value of Z. So we'll be getting 4.43 amps. So we found out I. Next step is to find the power factor. So power factor is cos of phi, that is cos 67.36. You'll be getting 0.385 leading. So why is it called as leading power factor? So very important observation here. Angle of Z is negative, so whenever the angle of Z is negative, we will say it to be equal to leading power factor, and whenever the angle of Z is with respect to positive, that is with respect to lagging power factor. So very important observation to be noted here. So with respect to angle of Z, we can find it out whether it is leading or lagging, or there are other ways as well. So we'll only focus with respect to this in this particular problem. So it is leading power factor, or in other words, we can also say it to be leading, since the value of, if you carefully observe, the capacitance value in ohms is greater than the XL value. So XC is greater than XL. So if XC is greater than XL, we can say it to be equal to leading power factor. Or as I mentioned, it is negative. If it is negative, then it is leading. If it is positive, it is lagging. So this is an important observation. Step 5 is to find the active power. Active power formula is given by P is equal to VI cos phi. So substitute the value of V, substitute the value of I. We know the value of cos phi as well. We'll be getting it as equal to 392.28 watt. Our final one to find out is to find the reactive power, that is given by the formula Q is equal to VI sin phi. So substitute the value of VI and sine of the angle phi. You'll be getting it equal to be 940.39 volt ampere, that is VAR. So this is the unit of reactive power. So we have found all the data according to the given question. So these are the results with respect to the question. So follow these steps in a sequential manner and write each of these steps so that you will not get confused at any point of time. So you'll have a clear picture as how to approach these type of problems. I hope this problem gives you a clear understanding of how it can be solved. So in case you have any questions, feel free to reach out. So we'll go into our next problem. So our example 2 is a circuit consists of a pure inductor, a resistor, a capacitor connected in series. Again, they've mentioned that they are connected in series. When the circuit is supplied with 100 volt 50 hertz supply, the voltage across inductor and resistor are so and so. If the circuit takes a 10 ampere leading current, calculate value of inductance, resistance, capacitance, power factor, and voltage across the capacitor. So some of the important observations they have themselves mentioned that 10 ampere leading current, that means it is highly capacitive than compared to inductive, that is XC is greater than XL. So that is one of the most important observation with respect to it. And apart from that, they've given the voltage across the inductor and the resistor. So we'll get started off with our problem. We'll be writing the given data. They've given V 100 and frequency equal to 50 hertz, VL 240 volt, VR is 90 volt, and I is 10 amps. Very important step is to write the given data. Always have a practice of writing them so that you will not go wrong while taking these data properly from the question. So this is our circuit diagram. 100 volt 50 hertz is represented here. Voltage across the resistor is 90. Voltage across the inductor is 240, and voltage across capacitor is not given. Current flowing through the series circuit is 10 amps. Now we have to find the inductance, resistance, and capacitance. So in order to determine, so our first step is to determine the value of R, L, and C. R can be straight away found out. That is VR is equal to VR is equal to I into R. So R is equal to VR by I. Substituting, you will be getting 9 ohms. XL is equal to VL by I. Again, Ohm's law. VL is equal to I into XL. So XL is equal to VL by I. 240 by 10, you will be getting 24 ohms. So we found out the value of R. We found out the value of XL. So we'll be finding out the value of Z. So when reason why we are following this step is because once we know Z and XL and R, we can find the value of XC. From that, we can find the value of L and C respectively. So Z is given as V by I, supply voltage is 100 and current flowing is 10 amps, so we'll be getting 10 ohms. So we know for a series RLC circuit, the impedance offered is equal to Z is equal to square root of R square plus XC minus XL square. So we will be substituting the value of Z, R square, and XL square, XL value. Once we have substituted that, we'll be simplifying it. You will be getting the value of XC, that is equal to 28.36 ohms. So we have the value of R, we have the value of XL, we have the value of XC. From XL value, we can find the value of L, that is XL is equal to 2 pi FL. Substitute the values of all of them, and you will be getting the value of L, that is equal to 0.076 Henry. We know that XC is equal to 1 by 2 pi FC. Substitute the value of XC, and you will be finding the value of C, that is 112.24 microfarad. So our first step is to determine R, L, and C is found out in this case by following these steps. Our next step is to find the power factor of the circuit. So how do we find the power factor of the circuit? I am considering an impedance triangle. So from here you can write cos phi is equal to, power factor is defined as the cos of the phase difference between the current and voltage. So power factor is equal to cos phi. So from impedance triangle, can we write power factor as equal to R by Z? So cos phi is equal to R by Z. So that is why I've written in this particular fashion. Once that is done, substituting the value of R and Z, you will be getting zero point 0.9. The reason why it is leading is very simple. They have already given in the question as well that it is leading, the current is leading, and it is highly capacitive in nature with respect to inductance value that is compared. So that's the reason why we'll be saying leading. And without this, power factor does not give any significance. So be very careful while representing it. So you have to mention this in case of series RLC or RL or RC circuit, any circuit for that matter. Step 3 is to determine the voltage across the capacitor. So how do we find it? We know that VC is equal to XC into I, that is I into XC from Ohm's law. So impedance offered with respect to capacitor is XC. So substitute the value of I and XC we have already found out earlier. You'll be getting 283.6 volts. So we have already found all the required with respect to the question that is asked. So these are the series of steps that we need to follow with respect to finding the given answer with respect to the given question. So I hope this problem problem is clear, so we'll go into our next problem, that is example 3. All right, our next problem is that is with respect to example 3. A circuit takes a current of 3 amps at a power factor of 0.6 lagging when connected to this particular supply. Another circuit takes a current of 5 amps at a power factor of this much when connected to the same supply. So if two circuits are connected in series, calculate current, power consumed and power factor. So very important observation, two circuits are connected in series, lagging and leading power factor are there. So individually they are there with respect to the circuits. That means it is supposed to be series RLC circuit. So let's get started with this problem. We'll be writing the given data, that is current I1 is equal to 3 amps, power factor 1 is equal to 0.6 lagging, V1 115 volt, I2 is 5 amps, and the power factor 2 is 0.707 leading, and V2 is equal to 115 volt. So they're connected to the same supply, so that is what is mentioned. So this overall supply voltage is equal to V, that is equal to 230 volt. uh, you will be getting for circuit 1, we will be finding the value of phi 1, that is cos inverse of the value. You will be getting 53.13 degree. We'll be finding the value of Z1, that is equal to V1 by I1. Substitute the value of V1 and substitute the value of I1, you will be getting 38.33 ohms. So Z1 is represented in terms of magnitude and angle, you will be getting this particular value. Similarly, I'll be finding the value of Z2. So why I'm doing this, I'll be finding the value of Z1 bar, I'll be finding the value of Z2 bar, and since they're connected in series, I can add them up, and then I can start off with finding current, power consumed and power factor. So similarly for circuit 2, phi 2 is equal to cos inverse of 0.707, 45 degree you will be getting. Z2 is equal to V2 by I2, substitute you will be getting 23 ohms. Z2 in polar, that is Z2 in polar form, it is represented, that is with respect to magnitude and phase angle, that is 23 at an angle of minus 45 degree. So this is the value of Z2. So once we know the value of Z1 and Z2, since they are connected in series according to the given data, we'll be adding them up. That is Z bar is equal to Z1 bar plus Z2 bar. Add them, you'll be getting 41.82 at an angle of 20.14. So now they've asked us to find the value of current. So current is given by I is equal to V by Z, straightforward from Ohm's law. You'll be getting 5.5 amps. So second one is to find the power consumed. We know that power consumed is nothing but the active power in the circuit, or if they ask you power loss, or what is the power that is taken in the circuit, or in any particular way, power consumed, power loss or something in those statements, then it is always active power, because the active power is the actual power consumed in the circuit. That is the reason why we will be saying that. So P is equal to VI cos phi, substitute the value of V, substitute the value of I. Cos value with respect to phi, we know that phi is with respect to impedance, overall impedance of the circuit, 20.14. This thing, since it is positive, it is always leading power, lagging power factor, and if it is negative, then it is leading power factor, as I told you with respect to problem 1. So you'll be getting 1.187 kilowatt. So next step is to find the power factor. So power factor is cos phi, cos of 20.14, so you'll be getting 0.939. As I told you earlier, the angle with respect to Z, if it is positive, it is lagging; if it is with respect to negative, then it is leading. So it is already explained in example 1 as well. So very important aspect. So we have found out all the given requirements with respect to this problem. So I hope the approach for this type of problems is clear. So I'll go on to our next problem, that is example 4. Two impedance Z1 and Z2 having the same numerical values are connected in series. If Z1 has power factor of 0.866 lagging and Z2 has a power factor of 0.8 leading, calculate the power factor of the series combination. So right now I'll be writing in the data with respect to the power factor 1 and power factor 2. Now pause this video here and try to solve this on your own. So majority of the students will do mistake at some point in the circuit. I'll tell where is that mistake will be done. So now we'll be continuing with our analysis. So they've given Z1 and Z2 to be equal, so I'll be considering that as to be equal to Z as a variable value. So phi 1 can be written as cos inverse of 0.866, that is given value. So we'll be getting 30 degree. Similarly phi 2 will be getting 36.87 degree. Z1 is nothing but Z at an angle of phi 1, so I don't know the value of Z, so I'll be representing it as Z itself, and 30 degree with respect to phi 1. So convert them into rectangular form. How do you do that? 1 at an angle 30, if you write it and convert it into rectangle, you will be getting this value. So I've represented z in both the real part and the imaginary part. Similarly, z2 bar is given as z at an angle of minus phi 2. It is minus phi 2 because it is with respect to leading power factor. That's why I mentioned as minus phi 2. So z at an angle of minus 36.87. Many of the students do mistake by substituting the value, that is you have to substitute minus phi 2 here. So that is one of the commonly made mistakes. So substitute and substitute for 1 at an angle of minus 36.87 in calculator and see what is its equivalent value in rectangular form. You'll be getting 0.8 minus j 0.6, but z is as usual there, so I'll be representing z in both real and imaginary parts. So once this is done, since they're connected in series, can we write z is equal to z1 plus z2? So you'll be getting 0.866z and add this equation and add this equation. So both of them, once they're added, you will be arriving at this particular point that is equal to this equation. So take z common and substitute and represent this particular rectangular form into polar form. You will be getting 1.668 at an angle of with z at an angle of minus 3.43. So this is the angle. So power factor is equal to cos of this angle. You will be getting 0.9982. So one of the commonly made mistakes by students, what students assume is that they will be finding z1 in polar form, that is z at an angle 30, z2 at z at an angle minus 36.87. Difference between z1 and z2 will be assumed as the power factor. Most of the students do these type of mistakes as well, so be very careful. Since they have given it a series combination, we have to add the total impedance and then represent them in polar or rectangular form and then find the angle with respect to them and then find the power factor. The reason why I'm taking directly plus 3.43, because cos of minus theta or plus theta, it is always cos theta. That is the reason I have not mentioned that here. But this is the approach with respect to example 4. I hope this problem is understood. So we'll go into our next problem, that is example 5. A coil of 3 ohm resistor and an inductance of 0.22 Henry is connected in series with an imperfect capacitor. When such a series circuit is connected across a 200 volt 50 Hz supply, it has been observed that their combined impedance is 3.8 plus J 6.4 ohms. So calculate the resistance and capacitance of the imperfect capacitor. So in these type of problems, what we have to do is that we have to draw the circuit diagram in order to understand how it can be analyzed. So it's a different type of a problem. So first up, we'll write the given data, that is they've given the small value of R, that is 3 ohms, and inductance of 0.22 Henry. V is 200 volt, F is given as to be equal to 50 Hertz, and Z is equal to 3.8 plus J 6.4 ohms. So this is the coil, this is the imperfect capacitor, that is R and Xc is it is mentioned that the imperfect capacitor will definitely be having some sort of resistance. So they've given the coil resistance, that is 3 ohm, and inductance value. So we'll be knowing the XL value as well. But they have not mentioned the value of the XC value or something with respect to R. So they've only given us the overall impedance, that is Z. So how do we approach these type of problems? So pause this video and try this on your own. If not, then please do watch it and understand how it can be solved. So our first step is to determine the resistance. So how do we do it? Z bar is given as to be equal to 3.8 plus J 6.4 ohms, isn't it? So XL is equal to 2 pi FL. So we will be knowing the value of XL, and we will be substituting that with respect to Z bar. If you see Z bar, the overall impedance of the circuit is nothing but R, that is 3 ohms. I've substituted 3 ohms here, plus J into XL, that is XL is found to be equal to 69.12, substitute it over here, plus R minus J into XC. So we don't know the value of R and we don't know the value of XC. So add the real parts together. This is the real part, and add the imaginary part together. Take J common and represent it here over here in this particular fashion. So I'll be labeling this as equation 1. So I'm considering it in the next slide as well. So now this will be labeled as equation 1. So given with respect to the circuit data, that is Z bar is equal to 3.8 plus J 6.4 ohms. This is our equation 2. So one of the most common observation here is this is the real part, this is the imaginary part. This is the real part, this is the imaginary part. So how do we find the resistance value? So both are both the terms LHS value is Z bar. So we can equate the real parts and we can equate the imaginary parts. Equating the real parts, we will be getting the resistance value, that is 3 plus R, that is equal to 3.8, you'll be getting the value of R that is equal to 0.8 ohms. Now equating the imaginary parts, we can find the value of Xc, isn't it? So equating the imagining is to our step 2 is to determine the capacitance. Equating the imaginary parts, you will be getting the value of Xc. So Xc is equal to 1 by 2 pi Fc. Solving this, you will be substituting the values, you will be getting the value of C that is equal to 50.75 microfarad. So this is how we have to approach this problem. They have asked us to find the resistance, they've asked us to find the capacitance, and we have done both of them. So I hope this problem is understood. So once this is done, I'll go into my next example, which is the final one, example 6. A series RLC circuit has a current which lags the applied voltage by 45 degree. So I lags behind V by 45 degree. The voltage across the inductance has maximum value equal to twice the maximum value of voltage across the capacitor. Important observation. Voltage across the inductance is 300 sin 1000 t and R is equal to 20 ohms. Find the value of inductance and capacitance. So how do we approach this problem? So we will be writing the given data. They've given us 5 to be equal to 45 degree, and they've mentioned that the current lags behind the applied voltage by 45 degree. That means it is inductive in nature, more of inductive in nature, that is XL is greater than XC. That is what they're trying to say with this particular statement. So we will start off with the problem, but one important observation with respect to the given data: the voltage across the inductance, that is VL max, has a maximum value, so we are representing it as max, and it is equal to twice the maximum value across the capacitance, so 2 times VC. So representing in this particular fashion. So how is this helpful? In order to determine the inductance value at the first place, we'll be considering this equation: VL is equal to 2 into VC. We know VL is equal to I into XL, so I'll be writing that. We know VC is equal to I into XC, substitute that as well. We know I and I gets cancelled out in this equation. You'll be getting XL is equal to 2 times XC. Important observation. So label that as equation 1. We know from power factor formula cos phi, that is with respect to impedance triangle, cos phi is equal to R by Z, isn't it? So cos phi, cos of 45 is equal to 20 by Z. So substitute and find the value of Z over here. So the value of Z is very important because we know the value of R as well. So we'll be able to find the inductance XL value from that. So we know for a series RLC circuit, Z is equal to square root of R square plus XL minus XC whole square. So over here we will be substituting XL is equal to 2 times XC, and we'll be solving this equation. We'll be getting the value of square root of 400 plus XC square. So squaring on both sides, and the root gets cancelled and this becomes squared up, and solving you'll be getting XC is equal to 20 ohms. So if XC is equal to 20 ohms, then XL is equal to 2 times XC, and it is equal to 40 ohms. Now they've asked us to find the inductance value. So we know that XL is equal to omega L, that is 2 pi FL. Substitute the value. Omega is given, so substitute the value. Omega is given from the equation, that is 1000 t. In terms of that, it is written, so 440 is equal to 1000 into L. So substitute and you'll be getting the value of L. So once we know the value of L, we can find the value of C as well, because Xc is known. So determine the capacitance. Xc is equal to 1 by omega C. So we know the value of omega, so substitute, you'll be getting the value of C, that is equal to 50 microfarad. So we have solved with respect to the given data. So we have solved various varieties of problem with respect to series RLC circuit. So any doubts with respect to any problem, feel free to reach out by typing in your questions in the comment section below. If you like this video, please do like this video, share it, and subscribe it to our channel for regular updates. Thanks for watching this video. Please do keep supporting. Thank you.